Hey guys, should be recording then. All working. Hey, yeah, so this is the micro problem set number 2. This one was quite easy, so this shouldn't be too long of a video, but hopefully this is helpful. I'm doing it, this is at 1:47 a.m. just to get this out of the way so I don't have much to do tomorrow, but this will be quick, so I'll just go through it quickly. So, let's look at here. So we have the game given in extensive form below, so we'll do question 1 now. We have the game in extensive form. And we're supposing that they're playing it twice, and when they finish. Also, if you want these in more detail, I think they're done also in the demonstrations, but I'm just going to give my sort of look at it. Payoffs in the twice repeated game are the sum of the payoffs in each individual game. What is the Nash equilibrium of the game played once? Well, if we just look at the game right there, we can see that 2, if we use backwards induction, 2 is always going to pick the right option, because 3 is better than 1. And then 1, knowing this, will also pick the right option, because 3 is better than 2. So the Nash equilibrium lies at right, as I say that. The twice repeated game looks like this. I'll zoom in so you guys can see that. Okay, you guys can see that? Hopefully that should be all good. And you can see sort of how we're basically repeating our tree, so we get our outcomes at the end here. So these should be all your payoffs. Do let me know if you disagree or don't think that this is how it should be. But this is what I got. So these are the payoffs. So we've got nasty teeth tonight. Then for our third question, you can see over here, calculate the number of pure strategies each player possesses in this extensive form. So to calculate the number of pure strategies, all you really need to do is look at the nodes, essentially. So your number of pure strategies are the number of points where you can make a decision. So you can see on this tree that 1 makes... Oh, I'll zoom in a little bit more. There we go. Hopefully that can be seen. 1 makes a decision 4 times. 1 makes a decision here, 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 and here. So 1 has 4 pure strategies. 2 also has 4 pure strategies, because 2 can make a decision here, 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 or here. And that's the deal. So each of them have 4 pure strategies. Okay, and then using backwards induction, find a Nash equilibrium to this game. So we have this graph over here, which I did for backwards induction. Okay, and you can see by using backwards induction, we get 6, 6. So what you do for backwards induction is simply put, you're going to find what's best in terms of outcome for that person. So for number 2 here, the best outcome is this one, because 4 is better than 2. And you continuously do that until you have a final strand that leads from the start to the end. And you can see here that the outcome 6, 6 is the best for everyone, actually. Actually, this is the Pareto optimal outcome as well, because this is the highest each person can get. So right will work every time, which is good for us, it makes it quite easy. But yeah, that's the deal. Okay, so for question 2, you're given 3 extensive forms, and you want to compile the strategic form for those games and find a Nash equilibrium for these games. So first of all, we're given this game here. Okay, so you can see the boundary here deals with an information set. So if I was to draw this out, I might do 1 there, and I'd do something like 1, 1 for my outcome here. But then I'd have these 2. 2 would be here, 2 would be here. I'd link these, and then 2 has 1, 0, 0, 1, 1, 0, 0, 1. That would be the extensive form. So thinking about it, okay, if I was to put this in strategic form, how would it look? So first of all, 1 has a choice of 3 actions, so left, middle, and right. So I'll do left, middle, and right here. And then 2 has a choice of 2 actions, left or right. So left and right. If 1 picks left, the outcome is going to be 1, 1 either way. So we'll put in 1, 1 in our table. Okay? Keep in mind, even if the 2's action here is irrelevant, 2 actually doesn't make a decision, but the outcome will be 1, 1 if 1 picks left. So that's the deal. If 1 picks middle, then we're looking at this one. Then 2 picking left would give us 1, 0, and 2 picking right would give us 0, 1. And the same is the case for right as well. So we have same here. Oh dear. Where's my keyboard? It's over there. There we go. So that would be how you would do it. In this case, you have, the Nash equilibrium here is just very clearly the 1-1, okay? Because if you do the underlining method with this, so let's do this more tangibly. What's the best column for each row? So best column for each row. So out of these two, for this one, it's going to be this, just one at the same time. It'll be left here and left here. And what's the best row for each column? So for this column, the best row is left. And for this column, the best row is left, middle, and right. So you can see that these two are just one Nash equilibrium. In fact, the left and right distinction doesn't matter. We can basically say that these two are the same thing. So we can see the Nash equilibrium will be here. Now this is fairly obvious actually, because why would one pick middle or right when one has a chance of getting either the same thing or worse? Because one would, if they played essentially middle or right, they would get either 1 or they'd get 0. But if they just play left, they get 1, which is, it's more reliable, essentially. So they play that, and that's the Nash equilibrium. So clearing the canvas. The strategy is very similar for the other ones. For the second game, it is a little bit different. It's a bit more extensive. We have a very similar game. I'll write it out again. Actually, screw this. I'll just go back and change the payoffs. There we go. Let's just rub this out. Okay. And we'll change the payoffs here. Is what's going to happen. Okay. So if we change this to 2, 0, 0, 1, 0, 1, 2, 0. It changes, okay? Still, if we use the underlining method, the pure strategy Nash equilibrium is still 1-1, because, again, it's not going to really work. But you can see here that 1 can actually gain 2 in some of these. So it's not necessarily optimal for 1 to always go for 1-1. So how can we sort of analyze this? Well, we can use a mixed strategy equilibrium instead. If I move down, we're going to draw out our graph again. So we'll use left, middle, and right again, and left and right. Same thing for the start. 1 gets 1, 1. It's all that sort of stuff. But here we're going to draw out 2, 0, 0, 1, 0, 1, 2, 0. Okay. Now via the underlining method, it would be pretty much just this again, which doesn't give us a conclusive one on pure strategies, but it does give us our 1-1 pure strategy equilibrium. But that's not really what we want. So if you guys remember, we calculated pure strategy Nash equilibrium by making it such that the player is indifferent between picking some of these things, given another player's random decision. So let's say 2 acts randomly between left and right, and let's say the chance of 2 picking left is Q, or actually no, not Q, P. The chance of 2 picking left is P, and then 1 minus P. Okay, and so let's take out left here because this wouldn't be in play. So we're gonna just take this out. Let's just say like the chance of this occurring is just 1, essentially, and then this one, essentially that. But yes, hold on, yes. The payoff here is 1, anyways, because in every case, if one picks left, the payoff is 1. But for here, you can see that, okay, if we times the payoffs here, we get 2 times P, 0 times 1 minus P, which gives us just 2P. And then we do the reverse here. We have 0 times P and 2 times 1 minus P, which is 2 minus 2P. Okay, and we need to make all of these equal to each other for 1 to be indifferent, which is actually quite simple. P is equal to a half, which makes all of these equal. So 2 times a half is, shockingly enough, 1, and 2 minus 2 times a half, so 2 minus 1 is 1. So If player 2 is indifferent, basically takes a random chance, half-half chance between left and right, then player 1 is completely indifferent between all of their strategies, because all of their strategies, on average, yield 1, essentially. So now we know we have 2 Nash equilibrium. We have pure strategy 1 at 1-1, and we have a mixed strategy 1 when 2 randomizes their actions evenly, essentially. The final one is actually pretty easy. Let me just rub this out. Oh, I'm just going to do this with a pen. That's better. Okay. We just switch around our payoff from this one to 1. And actually, we can just use backwards induction for this if we wanted to. So for 2, this is the best one here. Well, they're both good. Oh, well. Yeah. Well, that's a bit, yeah. So, yeah, for 2, let's try, yeah. Oh, yeah, sorry. It is actually better to do the underlying method for this. I mean, I've showed it here, so you can kind of just see it. But I'm just trying to show you guys how maybe you would do a backwards induction. Well, here, 2 can't distinguish between them. So let's just say, yeah, actually, no. You'd have to do subgame perfection in here, which you wouldn't be able to. Yeah, screw that. You guys can do it in the strategic form table. That's easy enough. You can see it's done here. I'll zoom in on it. Voila, I did it here for you. You're welcome. Okay, for question 3, this is a replication of question 5 from the other one. So I won't take too long with it, but let's just zoom in on it a little. Basically, let me just outline what the question is actually asking first. So the question asks this: a negotiation is organized as follows. At the first date, which sounds odd, it's like a union and a firm go on a date, and the workers kill the firm because a labour rising is coming. Who the fuck knows? At the first date, a union gets to propose a wage, and at the second date, the firm gets to agree. If the firm doesn't agree, if the firm does agree, the union gets the wage, which is just W, and the firm gets theta minus wage. If the firm refuses or rejects, they get negative delta, and the firm gets 0. Draw the game tree, essentially, and find a Nash equilibrium. So the deal is, for a Nash equilibrium to be in place, we must have a sort of situation where neither one doesn't change. So first, let's look at the one on the right. We have theta is less than W. So will the firm accept? Well, no. If theta is less than W, then their payoff will be negative. The payoff for the firm will be negative. And a negative outcome is worse than 0, so the firm will never accept this. So we know the union will never set the wage higher than the theta because they know it will automatically get rejected. For this case, where the theta is equal to W, the firm is indifferent, essentially. Because if theta is equal to W, then this equals 0, and this equals 0. So the firm is basically indifferent between either outcome. The only difference here is what the union gets, which realistically would sort of be beneficial to know to the firm, and would probably mean the firm would accept, but realistically, within the constraints of our model, we're assuming that the firm doesn't care about what the union gets, they only care about their own payoffs. So we're going to say that this is a weak strategy, because it basically just, so what did I write? It's accepting is just a weakly dominant strategy for the firm. So it's not great. But if the union proposes a wage lower than theta, then the firm will automatically reject it. And the firm, we can see that accepting the offer here is a Nash equilibrium for the firm, because if the firm rejects, they get less. And if the union changes their offer of the wage, they also get rejected. So union setting it lower than theta to start, and then the firm accepting is the Nash equilibrium. And that's the deal. Okay. That is all. I hope that was helpful. I've got to go to bed because it's 2 a.m. But I hope that was okay. I just rushed through it today because it was just sort of like a very quick and easy one. But yeah, hopefully that was helpful. When is this due, actually? The 29th? I think it's due the 29th. So good luck with that. All right, see you guys. Bye.